Alright, so welcome to section 3. In this section we're going to look at how to capture network traffic. But before we get into the demonstrations, we need to discuss a little bit of network theory. Modern networks are pretty efficient, and they have network devices that allow for segmentation of the network. Now this is great for throughput and performance, but it makes our lives a little more challenging when it comes to capturing network traffic. Firstly, in order to capture network traffic, you'll need to have a network card that will operate in promiscuous mode. When a packet is received on the NIC, it looks at the destination information. If the IP address or MAC address match the one that's assigned to that NIC, then the packet will continue up the OSI layers. If the destination address does not match, the packet is discarded. Promiscuous mode allows network cards to capture all packets that come across the wire, even if they are not destined for that particular host. And most modern NICs will allow for promiscuous mode. Next, we have to think about what hardware is present on our network. Most enterprise networks are made up of a multitude of hubs, switches, and routers. And in the context of packet captures, these devices segment the network in ways that prevent our sniffing host from capturing all packets that cross the network. Each device has its own special procedures for setting up a successful packet capture, and we'll discuss all of them in this lecture. Sniffing using a hub has to be the easiest way to capture all the traffic on the network. The way hubs are designed is that when a packet is sent from one host to the hub will send the packet out every port on that device. In the example here, host 1 wants to send some data to host 3. Host 1 will start sending data with the destination address of host 3. When that data is received by the hub will forward out all packet out each of the ports. Now this means that host 2 will see all the data being sent to host 3. Now if host 2 is not our sniffing host, then it will simply drop the packets and continue listening. However, if host 2 is our sniffing host, it will capture packets. It will capture every packet that is being exchanged between host 1 and host 3. Switches are much different when compared to hubs. They both provide the same result of connecting multiple devices together. However, switches are much smarter. Instead of sending data from one host out all the ports, it builds a table of what host is attached to what port. When data is sent from one host to the other on the same switch can tell that and will only send data out the ports for the destination host. So what this means for us is when we attempt to capture network traffic off the switch, we will only see the broadcast traffic or traffic that is specifically destined for our sniffing host. So to counteract that, we have 4 different methods for capturing packets off of a switch, and they are port mirroring, inline hubbing, using a tap, or ARP cache poisoning. So let's dive a little deeper into each one of these. Port mirroring is the first, and in my opinion, the most effective way of capturing traffic from a switch. This is a setting in most enterprise switches that allows an administrator to forward traffic from a particular host or all hosts out one port. In the example here, we have 3 hosts attached to the switch and 1 sniffer. When the hosts talk with each other, the sniffer wouldn't see that traffic. But if the administrator made the port the sniffer is attached to a mirroring port, then data from host 1 to host 2 would go to host 2 and to the sniffer. Or the administrator could assign the mirroring port to mirror all traffic. In that case, any conversation on the network will be sent from the source host to the destination host and to our sniffing host. And this is how many modern network intrusion detection systems work as well. So inline hubbing is a technique where you essentially place a hub in between one host and the switch. The sniffing host is then attached to the hub. So in our example, when host 3 sends or receives data, it must first go through the hub. As we learned a few slides ago, hubs forward traffic received out all of its ports. So not only would host 3 receive the traffic, but the sniffing host would as well. Now this method is particularly effective if you want to capture traffic to and from a single host. So in our example, any traffic between host 1 and host 2 would not be received by the hub because the switch knows that host 3 is on a different port and does not need that traffic. A tap is a device that sits in between the network and the device. It acts similarly to placing a hub in line, like we talked about in the previous slide, but it passes all the traffic between the network and the device in real time while also mirroring the data to the sniffing host. So there are two types of taps, aggregated and non-aggregated. Aggregated taps have a single mirroring port, and it sends that bidirectional traffic through it. On a non-aggregated port, it has two mirror ports, and one mirrors traffic from the switch and the other mirrors traffic from the host. This means that you would need two network cards on your sniffing host in order to capture all the traffic. So mostly aggregated taps are usually your best choice. However, non-aggregated taps are used when there's a high volume of traffic to and from the host, or when you only want to capture traffic from one side of the conversation. The final way of capturing traffic from a switch is a technique called ARP poisoning. ARP poisoning is probably not the best way to capture traffic because it involves creating a man-in-the-middle attack on your own infrastructure. ARP, or Address Resolution Protocol, is a way to map Layer 2 MAC addresses to Layer 3 IP addresses. In our example, host 1 had data to send to host 2. Host 1 has the IP address of host 2, but not the MAC address. So host 1 sends a broadcast to the entire network saying, "Who has this IP address? Tell me." Now host 2 responds saying, "I have that IP address, and here's my MAC address." Now the act of ARP poisoning inserts the sniffing host in the middle of that conversation. So take the example we just talked about. Host 1 needs to find host 2's MAC address. So host 1 broadcasts the ARP request, and instead of host 2 responding, our sniffing host will actually say, "I have that IP address and here's my MAC address," effectively impersonating host 2. When data is sent to host 2, it's actually sent to the sniffing host, and then the sniffing host forwards the data on to host 2. Now this is not the most effective way of sniffing traffic off of a switch, because it means that ARP must be enabled on your network, and could potentially slow down communication between hosts, because the sniffing host now needs to forward the traffic it receives to the correct host. So we've finally come to placing Wireshark on the network in order to sniff traffic destined for the router. In this scenario, it's important to understand the flow of your network as well as the topology. If you're trying to troubleshoot network connectivity issues between nodes connected to router 1 and nodes connected to router 4, you may need to place a sensor between each of the routers. Routers will not forward traffic that is destined for the LAN, and you will therefore only receive data that needs to be routed from network to network. So make sure you understand your network topology, and that will help you to place your sniffer in the right location. So we discussed a lot in this lecture. We talked about sniffing on a hub network, a LAN connected by switches, and a WAN connected by routers. In the upcoming lectures, we're going to go over how to initiate your first packet capture and how to filter the results you get. Future lectures in this section assume that you know where to place Wireshark.